We'll be working on 3.4 today, and we need to remember how to factor. If I had the quadratic x squared plus 5x plus 4, we would factor this using the box. X squared and 4. What's the next step? Multiply the x squared and the 4 together, and I get 4x squared. And then I factor 4 into all of its prime, well, in all of its factor pairs, 1 and 4 and 2 and 2. But the fact that that last number is 4 tells me something about the factors I choose. They're either both positive or they're both negative. And then I'm looking for factors that add to be 5. Is there a factor pair that will give me positive 5? 1x and 4x. So positive 1x and positive 4x. And then I look at the top row. What does the top row share? An x. If I pull an x out of each of those, I'm left with x plus 1. And if I pull an x out of the 4x, I get plus 4. So my factors are x plus 4 and x plus 1. Okay. What are the roots? Or the zeros? -1 and -4. Does everybody know how to do that? Now, in this case, do I need the box? Can you factor this without the box? Let's try one. X squared minus, let's say 2x minus 24. Can you think of two factors that multiply to be -24 and add to be -2? -6 and +4. What are the roots? 6 and -4. Is there anybody that can't do that? Okay, good. When do we have to use the box? When we have a leading coefficient. Let me see if I can find one. Well, let's do this one. 5x squared plus 30x plus 45. I can take a 5 out of that one, and I get 5 times x squared plus 6x plus 9, and that turns into x plus 3 and x plus 3. Does that make sense to everybody? And you might as well just write that one like this. 5 times x plus 3 squared. Does the 5 affect the roots? No. The roots are -3 and -3. How can -3 be the same root twice? No, positive and -3 are different. What about x equals -3 and -3? That's a bounce on the x-axis. So that equation over here at -3, it bounces off. And you can see the green parabola has 2 roots, 2 roots, 2 roots, and right before it ends up with no roots, that's what we call a duplicate root or multiplicity 2. Whenever a root happens twice, it just bounces off the x-axis. If it happens 3 times, then it does that weird x to the 3rd thing through the x-axis, and 4 times would be a bounce. Okay? So that one we didn't need the box. But let me see if I can find one where we do. What about 3x squared minus 11x minus 20? Can I pull out a 3? No. 3 does not go into 11 or into 20. And I still need to factor it, but I have a leading coefficient. Whenever you have a leading coefficient, you have to use the box. Some of you know another way to do it, but if you do, go ahead and use it. If we put this in the box, the 3x squared goes here, and the negative 20 goes here. Now what do I do? Multiply those together, and I get negative 60x squared. And I look at the factors of negative 60, and I try to create a negative 11. 1 and 60. Will that do it? Nope. 2 and 30. Nope. 3 and 20. Nope. 4 and 15. There it is. It's going to be 4 and negative 15. Doesn't matter where I put those. So 4x and negative 15x. What does the top row share? X. And if I pull an x out, what's left? 3x plus 4. And if I take a 3x out of the 15x, get negative 5. My factors are x minus 5 and 3x plus 4. So we need to set each of those equal to 0. The first one's easy, it's just 5. And the other one, we subtract 4, and then we divide by 3. And I get negative 4 thirds. Why did I get a fraction here? How did I know at least one of my answers was going to be a fraction? Right, the leading coefficient. If the leading coefficient cannot be factored out, one or both of your roots will end up being fractions. Okay, it is possible for both of them to be fractions, but at least one of them has to be a fraction. Does anyone need to see another one of those? Are you okay with that? You want to see another one? Okay. Let me see if I can find one. 36x to the third plus 66x squared plus 28x. Can this be simplified? I can take out a 2 and an x. Right? Take out a 2 and an x. 2x times 18x squared plus 33x plus 14. Nothing else comes out. Now I need to do the box. And at least one of my answers is going to be a fraction. 18x squared and 14. Somebody do that. 180 plus... Okay. So 252x squared. Now I find the factors of 252 that add up to be 33. And I'm just going to use my calculator. 252. 2 is definitely not going to work. 3 is going to be way too small. I'm going to start with 4. Nope. 252 divided by 6. Does that add up to 33? No. 252 divided by 8. 8 doesn't even work. Divided by 12. There we go. 12 and 21. I put 12x in one box and 21x in the other. What does the top row share? They do share a 2 and a 3, but 6 is the biggest number. I pull out 6x. If I take a 6x out, what's left on top? 3x plus 2. And if I take a 3x out of 21x, I'm left with 7. And then you always should double check, is 7 times 2 equal to 14? Yeah, so I did it right. Right. If those two constants don't multiply to be that last box, you screwed something up. Yeah. I have three factors in this case. 2x, 6x plus 7, and 3x plus 2. The 2 does not create a root, but the x does. What is the root for that variable? 0. So x equals 0. What is the root for this binomial? -7/6. And this variable? -2/3. That help, Gus? Okay. So that's factoring quadratics. There are two other quadratics I'd like you to look at. What about x squared minus 9? How does that factor? Close. It's x plus 3 and x minus 3. This is a DOPS equation, difference of perfect squares. It has to be a subtraction, and it's x times x minus 3 times 3, and it turns into x plus 3 and x minus 3. So the roots would be plus or minus 3. All right? What about this? 25x squared minus 16. Is that a difference of perfect squares? 5x and 5x, and 4 and 4. 5x plus 4, 5x minus 4. What are the roots? Plus or minus 4/5. Okay. All right, what about this one? Oh, no. How is that going to factor? This does not factor. It's an addition. DOPS only works if it's a subtraction. There is a way to factor this, but we're not going to talk about it today. So this one does not factor because it's a plus. If it was a minus, then it would be 8x minus 1 and 8x plus 1. Okay. What about this? Let's do... Yeah, this one is not a DOPS either. How come? It has an x. Is 16x squared a perfect square? No. 16 is, and 16x squared would be, but in this case, you cannot multiply two numbers together and get 16x. So this one, we need to pull out a 4x. And I'm left with x minus 4. What are the roots? This one is 0, and that one is 4. Does that make sense? All right, now in your assignment, it's going to say factor, just factor. It doesn't want you to solve. So you can stop when you get to this level. Okay? No, you won't need to solve for x today. But we also need to look at factoring x to the third equations. Now, from what I understand, there are a lot of different categories of x to the third equations, and every category has its own factoring method. And the only one I've ever been taught, the only one I've ever seen in any algebra class, is one that looks like this. Let's do 2x to the third minus 20x squared plus 5x minus 50. And we call it factor by grouping. Well, yes, you group the first two terms together and you group the next two terms together. What do the first two terms have in common? 2x squared, and when I pull that out, what's left? Minus 10. Okay. Now, what do the second two terms have in common? 5, and what's left? X minus 10. And then, what does this have in common with this? X minus 10. So I'm going to grab the X minus 10 and pull it out front. So I yank out the X minus 10, and what's left? 2x squared plus 5. Okay, now that only works if the equation is created using a linear binomial and a quadratic binomial. And most x to the third equations are not that way. They would be 3 binomials together. So the chances of running into an x to the third equation that is factorable using grouping is very, very small. But it is a skill that you need to know. So if you see an x to the third equation, check grouping. And if you group and this is not equal to this, you either made a mistake or it doesn't factor. Okay, let's try another one. Let's do x to the third minus x squared plus, minus 7x plus 7. I group the first two. What can I take out? X squared, and what's left? X minus 1. Okay, what can I take out of that? 7. And what's left? Negative x plus 1. Do they match? No. But could we make them match? How? Well, let's start this over. What should I take out? Negative 7. If I take out a negative 7, then this is x, and that would be negative 1, and now they do match. Because, so we're going to remove negative 7 there, and this is really negative 7 times negative 1. Together they make positive 7, but if I remove the negative 7, then the negative 1 stays behind. So every positive is actually 2 negatives. You can take a negative away from a negative and get a positive, but if you take a negative away from a positive, you get a negative. Now I pull these out, x minus 1 times x squared minus 7. Okay? I'm going to make one up. Let's see how good I am at this. 4x to the third minus 16x squared minus, sorry, this is going to take me a second, 18x minus 36. Okay, we'll see if that works. I group the first two. What can I pull out? 4x squared. We're just taking it out of these. Yep, just the first two. What's left? Okay. And then what can I pull out of that? Oh, hold on. I don't want 18. I wanted 9. Sorry. What? Negative 9. Why do I want to take out negative 9? So that the first parenthesis and the second parenthesis will match. So negative 9 times x plus 4. Now I yank out an O minus 4. So there we go. Okay. I now have x minus 4 times 4x squared minus 9. Can I go any further? This one is actually adopts x minus 4 times 2x minus 3 and 2x plus 3. So right here, this one. So I took this away, and I took this away, and I'm left with 4x squared minus 9. That's just the leftover when I factor out that binomial. All right? Okay. When I create an x to the third equation, every x to the third equation is actually the product of 3 binomials, right? So x plus 1, x plus 3, and x minus 4. If you take 3 binomials and you multiply them together, you end up with an x to the third equation, correct? So there should be a way to take an x to the third equation and simplify it down into its 3 binomials, and that's where we're headed. We're really good at doing that with quadratics, but x to the thirds are more complicated. So instead of going clear to the end, we're just going to practice a little bit of going backwards. If 24 is a bad example. Let's do 30. 30 is 2 times 3 times 5. Agreed? Well, if I divide both sides by 2, then that 2 cancels, and I get 15 equals 3 times 5. Right? So I should be able to divide this by x plus 1 and divide this by x plus 1, and my answer is going to be equal to x plus 3 and x minus 4. Right? Okay. But what happens when you divide by a number and it doesn't go in evenly? You get we get a fraction that comes from the remainder, right? So if I had, if I divide by the wrong binomial, I'm going to get a remainder. So we're going to practice dividing and seeing, is this number a fraction? Or sorry, is this number actually a factor? So if I had a really big number and I divide it by 5, how do I know that 5 goes into it or not? If I have a remainder, it does not. If I don't have a remainder, it does. Does that make sense to everybody? Okay. The same thing is true with binomials. So if I had, let's say, 3x to the third minus 28x squared plus 29x plus 140, and I wanted to know, is x plus 7 one of the factors? What am I asking? When I say, is x plus 7 a factor, what do I mean? Well, this x to the third equation is 3 binomials multiplied together. Is one of those this or not? So how do you tell? You just divide them. You divide by x plus 7, and how do you know whether x plus 7 belongs or not? If the remainder is 0, the answer is yes. If the remainder is anything other than 0, the answer is no. What are we really asking? Well, right, x plus 7, we set it equal to 0, and we get x equals negative 7. What does negative 7 tell us? Where does the graph hit the x-axis at negative 7? So really what we're saying is, if we were to graph this function, does it hit at x equals, oh sorry, wrong side, x equals -7. Okay, and all of this information is tied together, so let me make sure you understand it. We have a polynomial that is created using 3 factors. We multiply those factors together, we get the polynomial. The question is asking, is x plus 7 one of those factors? Which is exactly the same thing as saying, does the graph hit the x-axis at -7? And we can answer all of those questions by doing division. And you can either do long division with the box or synthetic division when it applies. Does synthetic division apply in this case? When can you use the shortcut division? When it's x plus a number or x minus a number. So I'm going to stick -7 in the corner, and I'm going to write down 3, -28, 29, and 140. Okay, drop the 3. -7 times 3 is -21. -49. What is -7 times -49? Hang on. Let me make sure I didn't write this down wrong, because this is getting really big really fast. 3x squared minus 28x plus 29 plus 140. Oh, yeah, okay. What is -7 times 49? Wow, this is a terrible problem. Oh well. Add those together. 372. Now I multiply those and I get negative 2,604. Wow. So that's going to be negative 2,464. Did that work? No, not even close. And here's another interesting piece of information. The graph does not hit the x-axis at -7. Everybody understands that, right? Okay. We have 3 factors. None of those factors are x plus 7. The graph does not hit the x-axis at -7. So where is the graph at -7? And the answer is that number. So if we were to graph that and plug in -7, the answer would be way down at 2,464. Okay? And that's what polynomial division tells us. It asks, is this a factor of the original problem? And we found out no. Does the graph hit the x-axis at -7? And we found out no. And where does the graph exist at -7? Way down at -2464. So if this ended up being 0, where is the graph at -7? At 0. So this point right here is -7, 0. Now in the graph that we just did, right, it's way down there. So I don't know how we... At -7, to find the answer, we have to go clear down to 2,600 and something. Okay? That really was a terrible problem. Usually they're closer than that. Let's do another one. 8x to the 5th minus 58x to the 4th plus 60x to the 3rd plus 140. And I want to test x minus 6. I have to be careful in this case. How come? With division, leading coefficients don't matter. There's no x squared term and there's no x term. So what number do I put in the corner? Positive 6. And my coefficients will be 8, -5, 60, 0, 0, and 140. Everybody understand why I have those zeros? All right. Drop the 8. 48. 43. Holy cow. Who wrote these problems? That's 258. All right, 318. Oh my goodness. 1908. Oh wow, this is going to be huge. Okay. 448. So 11448. 68688 and 68688. Oh my goodness. All right. Is x minus 6 a factor of that polynomial? No, because we did not get remainder 0. Wow. I really can't believe they did that to us. Let's try one more and see if we can get one that actually works. 48x to the 4th plus 36x to the 3rd minus 138x squared minus 36x, and I'm going to test x plus 2. What number goes in the box? Negative 2, and my coefficients will be 48, 36, negative 138, and negative 36, and 0. All right. 48, I have a bad feeling about this. So that would be negative 98. Oh, 96, thank you. Negative 96, which is negative 60. 120. Oh, this might actually work. Negative 18. So 36, 0, 0, or not 0, sorry. Yeah, that's right. 0. So x plus 2 is a factor, and x minus 2 is a root. So I know that x plus 2 is one of those binomials that was used to create the equation. And if we graph the function, it will hit the x-axis at negative 2. Okay? Okay, so in exercise 39 through 44, you're going to say yes or no. You're going to do the division and say yes it is or no it's not. And then 45 through 49, you say, you show that yes it is. How do you demonstrate that it is a factor? You just do the division and show that the remainder is 0. Okay, we're going to do, so 3.4, and let's do 5 through 63 odd. And we might have to go into tomorrow. We'll see. 5 through 63 odd. On numbers 51 and 53, you're just going to match them to the graph. How are you going to match them to the graph? You know the roots, so you can just match the roots to the equation and how many roots that equation has. All right. Good luck.